Today for our second day of probability, so we're on day 2, we're going to take a look at Venn diagrams, a method that can help us with some pretty challenging probability problems. So let's take a look. Let's say in this math class there are 30 students, 32 students, and let's say there are 20 juniors. So if we were to draw this in a Venn diagram, this whole area represents our class. I could put a circle here, and if this is our juniors, I could put 20 in here. So that's juniors. So outside this circle, there would be 12. So if we say the probability of A happening, and let's say A is the set that you're a junior, we would say it's 20 out of 32. The complement would be, you'll see it as the probability of A prime. That would be that you are not a junior. So we would have 12 out of 32. So that's kind of the first vocab, and you've seen complement and angles. And angles, they add up to 90, and probability here, the complement adds up to 100%. So let's say in the same class, so there's 32 students, there was 20 that were juniors, there were 15 that play a sport, and then there were 10 that were juniors and play a sport. So if we were to draw this diagram now, we would have circles overlapping. Here's our juniors, here's our sport circle. So there are 10 that are in both. Since there's 20 juniors, that's 10 juniors that don't play a sport. And there's 5 out here, so 25. So we have 7 students out here. So the intersection, the way you see intersection is probability of A intersection B. So A would be that you're a junior. B would be that you play a sport. So intersection is like an and, the probability that you are a junior and you play a sport. So that would just be 10 out of 32. The union, that's like saying or, and this is the, you see this is the probability of A union B. So that both of them, that would be 10, 20, 25 out of 32. And I think we already did that one, so let's take a look at this one here. And this is where it's kind of nice. When you look at these probability questions with all these words here, it's tough to figure this out because we have 30 students, 17 play computer games, 10 play board games, 9 play either. Find the probability that a student plays a board game. Well, that one's pretty easy, but if you had play a board game but not computer games, that's a little difficult to figure out. But this Venn diagram, it makes it really easy. So there's 30 students, so we have computer games and we have board games. And we just have these numbers here. We know 17 are in this circle, 10 are in this circle, and well, we know 9 are out here, and 30 total. So we don't know this intersection, so we could put an X right here, but we know 17 play computer games. So in this whole circle, there's 17. So this must be 17 minus the X. And over here, this must be 10 minus the X. And now we could figure out X, because 17 minus X plus 10 minus X, that has to equal 21 here. So we could solve this, so we have 27 minus X equals 21. Well, X has to be 6. So now we can figure out these numbers. If this is 6, 10 minus 6 is 4, 17 minus 6 is 11, 17, 18, 19, 21, plus 9, so we have our 30 there. So we can set up an algebra equation to figure that out. So now we're asked to find the probability that a student chosen at random plays a board game. Well, how many are in the board game circle? Well, that's just 10 out of 30, which reduces down to 1/3. Find the probability that they play a board game, but not a computer game. So they're in the board game circle, but not the computer, so that would be 4 out of 30, which reduces down to 2 out of 15. So this next one here, this union, this or, there's a couple different ways of looking at it. If we were to look at this example here, how many play computer games or board games, we'd have 17, 21 out of 30. What they're telling us here is if we looked at this, we'd take our board games. They say the definition plus our computer games minus that intersection of them. So if we just had our numbers here, we'd have 17 play computer games, so we'd have 17 plus our board games of 10 minus our intersection, and we end up with that 21 again. What they're saying is we can just add them together, but we have to subtract that intersection so we don't count it twice. An easier example to look at might be looking at cards. A card is drawn at random from an ordinary pack. Find the probability that a card is a heart or a king. So we want a heart or a king. Well, there's 13 hearts, but there's 4 kings. But there's an overlap here. We can't count the king of hearts twice, so we have to subtract that 1 there. So we end up with 16 out of 52. If we look at our Venn diagram here, if you look at this, in here we have our king of hearts, then we have our other 3 kings hanging out here, and then we have, in this one would be the ace all the way through the queen. So we have 12, 13, 14, 15, 16. Whereas if we just added our hearts and kings, we're counting that king of heart twice. Alright, and then the last thing that we're going to look at for today. Mutually exclusive. This means that there's like no overlap. And our probability is 0. So if I said, what is the probability of on a dice, what if I said rolling a 2 or a 3? You guys would say 2 out of 6 or 1/3. We just add these together. 1/6 plus 1/6 is 2/6. In a Venn diagram, there's no overlap. You could roll a 2 or you could roll a 3. There isn't an intersection there.